Hi everyone, I am Gilberto Díaz-García and I will expose the dissertation of the project Population Dynamics for Discrete Wasserstein Gradient Flows over Networks. This project has been developed with Professor Cesar Uribe at Rice University and Professor Nicanor Quijano at the University of Los Andes. This presentation will start with a statement of the problem that we try to solve and our concerns about current solutions. Then I will show our approach to tackle this problem. For this, we use two important concepts: Wasserstein distances over graphs and a relation between optimal transport in theory. Also, we present numerical simulations to illustrate our proposed algorithm. And finally, some concluding statements. The main idea is to find a way to optimize functions whose domain are discrete measures, specifically discrete probability distributions. However, these measures are supported on graphs, constraining how the agents can change mass between them. So, we need to define a geometry in the space of discrete distribution considers the constraints imposed by the graphs. With this in mind, we use the notion of optimal transport. With it, we can actually define a distance between two arbitrary measures. However, as you can see, this definition seems intricate and it's computationally expensive. Therefore, some applications are constrained to only find approximation of this notion of distance. However, when we only consider discrete measures supported on graph, we can reformulate Wasserstein distance like this. This formulation resembles the notion of distance as a minimal arc length between 2 points. Thus, we can access the notion of distance through a metric tensor. With it, we can redefine other geometric notions as the gradient, for example, to include the information about the graph in our optimization problem. Now, how the functions are minimized? We start by defining the gradient flow with the new metric tensor. However, it's interesting to note that it's equivalent to a game theory formulation. While in a gradient flow, we move towards the minimization of function f, in a Riemannian game dynamic, proof of population plays a game between them, moving towards the Nash equilibrium of a potential game. To develop an algorithm that minimizes the function f, we need to discretize the previous dynamics. From a game theory perspective, we can see it as choose a target distribution to move towards instead of choosing a direction. If we repeat this process iteratively, we can propose an update rule that moves towards a better distribution each time. This update can be summarized like this, where each agent exchanges mass with their neighbors in order to find the Nash equilibrium of the game, and therefore the optimizer of function f. An important feature of this update rule is that its convergence is guaranteed for a proper choice of the parameter gamma. Therefore, we develop an iterative algorithm that works with local information that minimizes function over discrete measures. To illustrate the performance of this algorithm, we try to transform a uniform distribution into a random distribution Q by minimizing the Kullback-Leibniz divergence between these. Also, these distributions are supported on Erdős range graph with 15% of probability to connect two nodes. Here can be noticed how the agents move towards the distribution Q that is represented by dots at the end of the plot. But instead of exchanging mass arbitrarily, they use the edges of the graph plotted at the left side of this slide. So, in conclusion, we have developed an algorithm that minimizes function over discrete probability measures. Also, using a different approach, this algorithm works with local information but can achieve similar results to other approaches. And more important, we provide mathematical support to ensure the convergence of this algorithm. Thank you.